Condition and structural monitoring provides complete monitoring solutions for a broad range of markets, including aerospace, offshore structures, storage tanks, wind turbines, cranes, pipeline pigging, surface transportation, systems and bridges. Structural health monitoring is concerned with the structure, whilst condition monitoring deals with the machinery, mainly moving components, gears, bearings and the like, but including boilers and heat exchangers. Encompassing the use of permanently attached sensors to collect data to analyse changes in performance or condition of a machine and provide real-time information on its condition, CSM offers objective and reliable data from which an assessment can be made to observe any changes to the health of the structure and assess the structural health of a component in the present, as well as providing a tool to safely extend the useful life in the future. Acoustic emission testing, vibration analysis and guided waves techniques can be used solely or in combination to monitor the performance of machinery or a component whilst in operation or offline. The CSM section also offers modelling, algorithm and software development, hardware design and testing to complement these techniques. The main advantages of acoustic emission are detecting damage in structures, identifying its location and permanently monitoring it. This optimises its maintenance and inspection interventions. Acoustic emission has been used in composite turbine blades. Initially, an attenuation analysis was conducted at NAREC to assess the wave propagation in composites. An acoustic emission source localisation test was also carried out. Acoustic emission is a passive technique and therefore is triggered by the defect energy release during crack creation and growth. As part of this project, fatigue tests have been conducted at NAREC with different loads and defect sizes. Actual data has been recorded for 12 days in total. In the results, acoustic emission activity is shown as a function of time. The increase in energy is often related with crack propagation. Acoustic emission techniques have also been used in cranes to prevent fatal failures. A modelling analysis based on finite element and statistical analysis was performed in the reinforcing plates of the crane, as they were identified as the most prone to damage. This analysis included modelling of acoustic emission in steel joining plates. Acoustic emission behaviour was also simulated in different material structures. An acoustic emission system to detect cracks on rotating parts of wind turbine machinery has been developed. A number of sensors and a data acquisition system have been used to detect fluctuations on the wind turbine generator. The system is a standalone acoustic monitoring system that can transmit data to a receiver and detect cracks on rotating parts. It allows for early detection and identification of defects of components of the wind turbine, such as slip ring corrosion and shaft bearing misalignment. Several sensors were used to evaluate the operational condition of the turbine's generator, gearbox bearings and main shaft, and wireless sensors for rotating parts. Data was gathered for the full speed operation range. Vibration analysis allows to do condition-based maintenance, monitor cracks and damage, permanent monitoring, and therefore optimise maintenance and inspection interventions. Following requirements from end users, structure and machine mock-ups have been designed. The prototype was used with integrated sensors and control hardware in order to simulate the operation and improve inputs to maintenance. Acoustic emission and vibration analysis monitoring software have been combined. Trending analysis has been performed with integrated acceptance criteria. Malfunctions of automatic train doors accounts for delays in train operations. A low-cost vibration monitoring system has been developed which allows predictive maintenance and hence providing a cost and operations effective framework for the train operators. Experiments have been carried out on East Coast train doors where the failure mechanisms are known to be bolt looseness and change in air pressure, which affects the speed of the door closing and hence causing delays. CSM have adapted the guided ultrasonic technique used for inspection of pipelines to detecting cracks and corrosion in chain links used to moor FPSOs. This has involved modelling with guided wave propagation in chains with excitation of multiple wave modes and the distortion around the chain beds. Because of the complexity of the A scans, an automated defect detection software has been developed to aid the interpretation. A procedure has been developed using a marinized transducer collar that shows sensitivity to slots of increasing depth machined in a 160mm chain. This was eventually demonstrated underwater on a chain climbing robot. A modelling analysis of guided waves based on finite element was performed in the reinforcing plates of the crane, as they were identified as the most prone to damage. Piezoelectric sensors have been designed for this project, with dual capability of transmission and reception of guided waves and acoustic emission. In the experiments, a crack is induced and its size is increased. The software starts the acquisition when an acoustic emission signal is received. Then the source of the signal is graphically shown. After that, a pulse is transmitted through the sensors to focus on the source and the signal is received by the sensors. The software shows the crack size depending on the error function, which is calculated from the signals received. As can be seen from these graphs, the probability of detection increases with the defect size until it reaches a limit value. Theoretical modelling is used in guided waves to model its acoustic behaviour. Having guided waves propagate in both directions simultaneously creates a problem, since the A scans will continue echo signals from both directions. By having two rings of transducers, the signal in the backwards direction will be cancelled and the signal in the forwards direction will be reinforced. By including a defect in the model which simulates a percentage of pipe wall thickness loose, the differences between signals responses can be compared. By increasing the size of the wall thickness loose, the reception signal amplitude will change. Experimental validation of results is key. To do so, an internal guided wave collar has been developed in order to validate the modelling results. A condition monitoring feasibility study of the use of guided waves was carried out. The condition of cable stays of a suspension bridge in the Netherlands was assessed in order to identify corrosion and cracks in the wires at an early stage. The main benefit of the technique is to detect breaks and corrosion of the subsurface strands of the wires.